Right, question 13. This is the diffraction grating question. But first, it wants us to basically look at and be able to explain diffraction using the Huygens principle. Right, so basically, this is the your standard diffraction diagram. We have plane wavefronts hitting a gap. First up, though, describe what's meant of a wavefront. Right, again, marks in the bag. This should be instant recall. Right, what's the definition of a wavefront? A wavefront, okay, is a line along which all the particles or points of the wave are in phase, are in exactly the same phase with each other. Okay? Don't say wavefronts are the peaks or don't say wavefronts are the troughs. That is incorrect. Technically, that's incorrect. Okay? The true definition is lines along which all the points or all the particles, if it's a mechanical wave, are in phase. So every particle or point along that line, that line, that line are all in phase. Okay. Add to the diagram to show Huygens construction, or how Huygens construction can be used to determine the shape of the next wavefront. Right. This is I hate trying to teach Huygens construction. It's very difficult. It's a really challenging concept. Once you get your head around it, it's fine, but to be able to explain it in an exam is really tricky. It's really tricky. However, they don't want you to explain, they just want you to annotate the diagram, which I think is very nice of them. Now, it even gives you a little hint by labeling 3 points A, B, and C on the diagram. Right, so what's essentially Huygens principle, Huygens construction, is that all the points along a wavefront act as though they are individual wave sources. So if they're individual wave sources, okay, we're just going to consider three here, otherwise the diagram's going to get too messy. Circular wavefronts are going to radiate out from that single point, aren't they? Same at B. Circular wavefronts, semicircular wavefronts, are going to radiate out from that point. Okay, so let's have a go at annotating. Right, the next wavefront, which has to be in phase, let's do A, it has to have the same, there has to be the same wavelength. Okay, so this distance here is the same as the distance to the next wavefront. Okay, but it's not going to be plane, it's going to be semicircular. So we'll go with this. There you go. Now, it's going to be semicircular, isn't it? So basically, it's going to look like that. Point B, the next wavefront's going to be there. Point C, the next wavefront's going to be there. So we can do the same here, can't we? Semicircular wavefronts going to radiate out. Okay. Now, in reality, we don't just have 3 points along this plane wave, A, B, and C. All the points are radiating out. Now, the resultant is all these semicircular wavefronts superpose, then interfere with each other, and essentially create destructive interference here, but constructive interference here. So here we go. So plane, circular at the edges. There you have it. Huygens construction, and why we get the distinctive diffraction pattern when waves travel through a gap. Simple. Okay, and we can even, you're not asked to do this, but just showing for educational purposes that you can continue with all the other wavefronts. There you have it, diffraction through a gap. Right, so that was the theory. Now, in practice, we've got, this is a diffraction grating. This is another of the core pracs, which you should know off by heart. So, let's have a look. Give a reason why a laser is suitable for this. Well, lasers are monochromatic. Okay, monochromatic means same frequency or same wavelength, so it's the same color. That's why we use lasers. Okay. So monochromatic is going to lead to coherent wave sources. Okay, that's what we need in this case. The wavelength has to be the same. Right. The student measured the distance between the central maximum and the third order. That distance to be 102 centimeters. So let's have a little look at this. Where's the central maximum? It's the brightest one. So there's the central. Now, N1, N2, N3. Okay, so that is N3. It was N3, wasn't it? Yes, the third order maximum. Okay. So this distance here is 102 centimeters. Right, what's the equation? Diffraction grating equation is n lambda is d sine theta. Right, what's d? Well, n is 3, isn't it? That's because that's the order. Okay, because we're using the third order maximum. Lambda's the wavelength we're trying to find. What's d? You can remember what d is. Well, d is the distance between adjacent lines on the diffraction grating. Now, we are given, not the distance, we're not given d, we're given the lines per millimetre. That's what you're given. That's how diffraction gratings are basically measured. So 200 lines per millimetre. So d, okay, is basically 200 lines per millimetre. So it's basically 1 millimetre, which is that in meters, divided by 200, because there's 200 of them. That's given us 0.000005 meters. Okay, be nice to get that to standard form, wouldn't it? 1, 2, 3, 4, 5, 6. So 5 times 10 to the minus 6 meters. Easy peasy. Right, we just need to find theta now, don't we? So a little bit of trig now. So let's have a look at this. What do we got? So we have the central maximum. We have n equals 3. We have the laser over here. Right. Now we're trying to find this angle theta, aren't we? Okay, so the laser is there. What a nice laser. Right, okay. So what do we know here? We know the distance. What distance is that? That was 1.02 meters. Distance from the board was 3 meters. So it's a cheeky bit of trig then, isn't it? It's we've got the opposite and the adjacent, so it's tan theta 1.02 over 3. That gives me a theta of 18.8 degrees. Making sure I set my calculator back to degrees there from the radians of earlier. Right, so then it's just putting those final values into the equation. Okay, we have, so 3 lambda, because it's n equals 3, equals d 5 times 10 to the minus 6 sine theta times sine 18.8 degrees. That gives us a wavelength 536.5 nanometers. Yep. Now that, from the table, is green. There you have it. Okay, diffraction gratings and the diffraction grating, core practical. We'll have a lovely bit of Huygens construction